This section is about the chi-square test for goodness of fit. So for our first example, in 2007, the M&M company reported the color distribution for M&M should be 13% brown, 14% yellow, 13% brown, red, etc. This is our proposed distribution. This is kind of our theoretical distribution. These are theoretical percentages of what it should be. What we want to know is we want to know if these proposed percentages are actually a good fit for our current M&M data. Or we might want to know if our current M&Ms have the same color distribution, if these percentages are a good fit for our data. To test this, we can take a sample of M&Ms and examine the color. So I took a sample of 74 M&Ms, so I just reached in, grabbed 74 M&Ms, and found this data. So we had 5 brown, 11 yellow, 11 red, etc. So this is our actual data for our current M&M sample. We could call this our observed counts, because it's observed of what I actually see in my data. So how would we decide if our current color distribution is the same as our 2007 distribution? Because looking at this 5, 11, 11, that doesn't really tell me if that's 13%, 14%, 13%. So there's some different ideas that you could have to compare this. So maybe we could compare our observed counts and expected counts. So maybe we could say, well, if I had 74 M&Ms and 13% are supposed to be brown, then how many should have been brown? Or maybe we can change the number of M&Ms to percentages and compare the percentages. So let's look at this. I have my number of M&Ms. I went ahead and changed it to a sample percentage. So 5 out of 74 is 6.7. 11 out of 74 is 14, etc. So these are my actual percentages. So this column is my actual. And again, this is my theory. So I was supposed to get 13% brown, but I only got 6.7. I was supposed to get 14% yellow, but I got 14.86. Well, that's actually pretty close. 13 and 14, that seems pretty close, but 20 and 25%, that seems a bit off. 24 and 24.32, that's really close. 16 and almost 13 and a half, that's a little farther apart. So we're not exactly the same, but I probably wouldn't expect my sample to be exactly the same as my theory. So how would we tell if the differences between our sample percentages and our theoretical percentages are due to sampling variability, just which sample I chose, or if the true population percentages are different from these theoretical percentages, because these percentages are the actual from my sample. I would have also actual percentages from my population, I just don't know what they are. And then we want to see if that matches our theoretical percentages. So I'll write some new notation. Okay, we would let like P1 be our population proportion of brown M&Ms, P2 population proportion of yellow M&Ms, and so forth. The status quo would be that our current color proportions are the same as the 2007. So that would mean my first proportion should be 0.13, my second proportion should be 0.14 for 14%, my third proportion should be 0.13 for 13%, and so on. So that would be the null. Our status quo is that all of these percentages are right. The alternative is at least one of our proposed probabilities is wrong. Because remember, if it's not that all of them have to be wrong, but as long as even just one is wrong, then this null would be false. Okay. So the alternative is at least one is wrong. Or sometimes we phrase the hypotheses as our 2007 color distribution is a good fit for our data. So the null is that it works. The alternative will be that the color distribution does not fit our data. So if 13% of the M&Ms really are brown, how many brown M&Ms would you expect in a sample of 74? Well, I would do 0.13 times 74, which would give me 9.62. So I would expect 9.62 brown, but I only got 5 brown. That seems a little low, but maybe it was just the sample I picked. So what we can do is we can make a table like this where we have our observed counts for brown, yellow, red, orange. We have our theoretical percentages, and we can find the expected counts for each one. So what I would do is my total here was 74. So I'll do each percentage, so 0.13 times 74, that's 9.62. My next one should be 14%, so I'll do 0.14 times 74, which gives me 10.36. My next would be 0.13 times 74 again, so 9.62. So pause it, see if you can fill out the rest of these by yourself. So 0.20 times 74 should give me 14.8. Okay, so I also get 17.76 and 11.84. Now, a good way to check that you've done this correct is to add all of these up. So put all of these in your calculator, add them all up, and I got 74. Your total here should match your total here. Okay, so your total shouldn't change. So these are all of the expected counts of what I would have gotten if these percentages were right. So these are expected counts if theoretical percentages are right. Now we need some way to compare our expected counts to our observed counts. The way that we found to do this is to use our chi-square distribution. So first, an introduction to the chi-square distribution. It's another common distribution. We use it quite often. It is not symmetric. It's very right skew. Oh, I said left skew. I meant right skew. And the shape depends on its v degrees of freedom. So you'll notice v equals 5 is very right skewed. V equals 10 starts to get a little more symmetric. V equals 15 gets a little more symmetric. But this never actually gets to where it looks like the normal distribution. It's not supposed to. It's a different kind of distribution. So now to compare our expected and observed counts, we have to compare them. So we use a chi-square test statistic. So we have this chi-square. This symbol is Greek for chi. What we'll do is we'll take each observed count, we'll minus the expected count. So we're trying to find the difference between the observed and the expected. But then if you got some positives and some negatives and you added them up, they'd cancel each other out. So that we don't want positives and negatives to cancel each other out, so we'll square each one. And then we want to scale it somehow. So if we were dealing with really big numbers, our differences would also be really big just because our numbers are really big. So we divide by our expected counts just to kind of scale it. Make sure, one of the biggest mistakes I see is people divide by the observed account. You're supposed to divide by the expected count. So you'll do each observed count minus the expected, you'll square it and divide by the expected, and then we'll add them all up. And we're going to have k minus 1 degrees of freedom, where k is your number of groups or categories, whatever you want to call it. So if our observed counts and expected counts are really different, what kind of numbers would you be expecting? Okay. Well, so observed counts minus expected counts, if they're really different, that will give me big numbers. So if our alternative is true, that our percentages are off, we'd be looking for big values of chi-squared. So this test will always be a right tail test. So every other time we've looked at our alternative to decide which tail it will be, this one will always be a right tail test, because if our percentages are wrong, we'll get big differences. So we'll be looking for big values of chi-squared. So our chi-square test for goodness of fit. We use this when we have a proposed distribution and we want to know if it's a good fit for our data. We want to know if our theoretical probabilities are correct. The total sample size is n, and our sample items are classified into one of k groups. So again, we want to know if our probabilities fit our data. The conditions is each of the expected cell counts are at least 5. That's how you tell if the sample size is big enough. The null, you can say it two different ways. You can say all the theoretical probabilities are correct, or you can say the proposed distribution is a good fit for our data. It means the same thing. The alternative is that at least one of our probabilities isn't correct, or the proposed distribution is not a good fit for our data. The expected count, we didn't actually write the formula up above, but what were we doing here? We were taking the percentage times our sample size. That was how we got our expected counts. So n is our sample size times our probability for that group. Oh, never mind, I wrote it here. So total sample size times theoretical probability for that group. Once again, our test statistic will be chi-squared equals the sum of all of our cells, but we'll do each observed count minus the expected count squared over the expected count. And our degrees of freedom is k minus 1. Remember, k is the number of groups. Our p-value is the area under the chi-squared curve to the right of our test statistic, because it's always going to be this right tail test. For our calculator, we're actually not going to do the entire test in our calculator because I just feel like it's more of a pain to try and type in. Your calculator is capable of doing it. You are welcome to try and figure out if you want. But I am going to use the calculator just to find my p-value, to find that right tail probability. So we'll be using the distribution instead of the test and looking for something that says chi-squared. Because it's a right tail test, you'll put your chi-squared value as your lower bound and then 1,000,000 or some big number for your upper bound. So let's try it. We want to know if our current M&Ms have the same color distribution as our 2000 distribution. We'll conduct the test with my data. And to find the expected counts, we already did that, so we don't need to do it again. We'll just use them from up above. So going through, alpha equals 0.05. Let's see, we need to check our conditions, which is that all expected counts are at least 5. Let's see, my smallest one is 9.62, so I'm good there. You need to write down your hypotheses. So the null will be that all the theoretical probabilities are correct. The alternative would be that at least one of the probabilities was wrong. You could also say, if you want, that the null is the 2007 distribution is a good fit for our current data. And the alternative is that the 2007 distribution is not a good fit for our data. Now for our test statistic, chi-squared is equal to the sum of, we'll do each observed minus expected squared divided by the expected. One of the reasons we're doing this by hand and not in your calculator is because I think this is probably one of the most common tests I've heard of people doing in the other classes, and they might want you to do it by hand. We're going to make sure that you can. Plus it's kind of good helping you learn the theory. So we'll take each observed, so 5, minus the expected of 9.62, square it, and then make sure you divide by expected, so 9.62, plus, now we'll take our next observed of 11, minus its expected, 10.36, squared, divided by 10.36, plus, my next one is 11 and 9.62, so 11 minus 9.62, squared over 9.62, plus, then we have 19 minus 14.8, squared divided by 14.8, plus we have 18 and 17.76, so 18 minus 17.76 squared over 17.76, plus, and we have 10 and 11.84. So 10 minus 11.84 squared over 11.84. The hardest part about this test is getting it all into your calculator correctly. Make sure you're using parentheses. Make sure you divide by the expected values. You should get 3.94. I often have to put this in my calculator twice or check it on the computer. I'll only make you do it usually with just a few cells on the test so that you have less chances to mess up. Or I'll often just give you the test statistics so that you can save time too. So I'll probably make you do one by hand on the test and then give you one test statistic to save time. So that's our test statistic. Now let's check degrees of freedom. So degrees of freedom is k minus 1, or number of groups minus 1. So let's come up and check. We have 1, 2, 3, 4, 5, 6 groups. So 6 minus 1 equals 5. For my p-value, I would have drawn my chi-square distribution. I have my test statistic is 3.94, and it's always the area in the right tail. So let's pull up our calculator. We want to do the distribution, so second distribution. I'm looking for a chi-squared CDF. Okay, a CDF has our cumulative probabilities. So I can put in my lower bound of 3.94. I can put in my upper bound of like 1,000,000 because it's supposed to be infinity, but we'll just do 1,000,000. We can put in 5 degrees of freedom. And it looks like this area is 0.558. So my p-value equals 0.588. That looks like a big p-value. And so for a big p-value, I fail to reject the null. So even though my observed counts were off sometimes, it turns out that it wasn't so far off that I'm going to think those theoretical percentages are actually wrong. Okay, so we didn't find any evidence that the 2007 distribution does not fit our data. Notice this is a double negative. It's just the way it is. Okay, so we did not find any evidence to say that it does not fit our data. I always think of this then as until further notice, we may as well keep using the 2007 distribution. If we didn't find any reason to think that it doesn't work, we may as well just keep using it. Let's try another example. The market shares for 4 microwave ovens are listed below. Okay. So these are our market shares in our current city. Or you could think of this as these are going to be my theoretical percentages. We want to expand our store to a new city. We want to know how many microwaves of each brand to stock. We assume that the market shares will be the same as our city. So kind of what we're assuming that would be our null hypothesis there. We need to know how many microwaves of, okay, so we know we want to know how many microwaves. To test this, we take a sample of 400 customers in the new city to see which brand they would buy. So that tells me n equals 400. These are our observed counts. These are our theoretical percentages. We want to conduct a new test to see if the new city has our same distribution as the old city or if it's going to be something different. Okay, so let's do our table of our observed counts. So 102, 121, 120, 57. And our theoretical percentages. our probabilities, we'll change into decimals. So 0.2, 0.35, 0.3, 0.15. Then we need to find our expected count. So remember, our expected is going to be equal to our sample size times its probability. And our sample size is 400. So 400 times 0.2 gives me 80. 400 times 0.35 gives me 140. And 120 and 60. Okay, so let's start our test. So let's check our conditions, which is the all expected have to be at least 5. Well, my smallest one is 60. We're definitely good. Let's pick alpha equals 0.05. Actually, just to mix it up, since we keep doing the same thing all the time, let's try 0.10. And let's pick our hypotheses. So null and alternative hypotheses. The null would be the market shares are the same, or the theoretical percentages are correct. The alternative would be that the market shares are different, or at least one theoretical percentage is wrong. Now, the fun part. Our chi-square test statistic is going to be equal to the sum of each observed minus expected squared over expected. Now remember, if you forgot this sum sign, that just means add everything up. So we'll take each observed of 102 and the expected of 80. So we'll do 102 minus 80 squared divided by 80, plus the next one, which is 121, minus its expected of 140, squared over 140, plus then let's see, we have 120 and 120, so 120 minus 120 squared over 120. Oh, that one is pretty similar. And finally 57 minus 60 squared over 60. So it looks like my first two were kind of off from their expected counts. The second set of two, number 3 and 4, were pretty similar. And this gives me 8.78. So that's my test statistic. My degrees of freedom is k minus 1. So remember, that's your number of groups. I have 4 groups, so 4 minus 1 gives me 3. For my p-value, here's my chi-square distribution. I have chi-squared equals 8.78, and I'm looking for the area to the right. So once again, pull up your calculator. We want the distributions because it's the chi-squared distribution. So we want chi-squared CDF. We want those cumulative probabilities, or the probability not just at one point but the whole area. So my lower bound now is 8.78. My upper is still a million. Degrees of freedom switch to 3. And it looks like my p-value equals 0.0323. This is smaller than alpha equals 0.10. So I will reject my null and have evidence for the alternative. So I would say something like, we have evidence that the market shares are different in the new city. At least one of the theoretical percentages is wrong. Notice this hypothesis test does not tell you which of the theoretical percentages are wrong or how many are wrong. Okay, but I can tell from looking up above, I could guess that it's probably 1 and 2 that are the wrong percentages because those observed and expected counts seem the farthest away. However, that's not what the actual test tells me. That's just kind of what I'm figuring out with my logic. This next example is for you to try, but I just want to mention real quick that it is a binomial. It's checking to see if a binomial distribution is a good fit for your data. This is probably one of the most common uses of our chi-square test for goodness of fit. It's checking to see if a famous or common distribution is going to be a good way to describe our data or our scenario. So in this case, we're checking to see if the binomial distribution would be a good fit to describe the number of boys in a family. So what you'll have to do for your theoretical percentages is you have to go back and remember how to find binomial probabilities.